So welcome to AUT-128 Station number 7. In this station, we're going to be dealing with automotive instrumentation systems, so essentially gauges. You should have on your packet this cover picture. It should look just like this. If you do not, then you need to head up to the front and get a new one, or you need to go back to the bookstore and buy it, or you need to print it out, depending on what your case is. So make sure you have the right packet for this station. It should look like it is on the screen. So learning task for this one. You guys have been through this song and dance a couple times now, so this should be pretty quick. Learning task. We're going to identify common gauges, the instrument clusters, and sending units. You should understand how common automotive gauges, sending units, and clusters operate, or how they work. And then 3, you should be able to diagnose and repair common gauges, sending units, and clusters. You'll be able to change them out, fix them, diagnose them, all that good jazz. Safety, as always. Instrument systems are low voltage. You need to be aware that anytime, again, you work around electricity, you can hurt yourself. Sending units placed inside the engine bay are typically hot and can be placed near moving objects. When we have to test some of these sensors, you're going to want to be careful because if the engines have been running, the sensors themselves are hot, or if we need to test the sensors while the engine is running, you need to be aware that you have belt drive systems, exhaust, all kinds of stuff moving around in there. So we're going to be very careful with our hands. Number 3, batteries do contain sulfuric acid, which is very dangerous to yourself and your belongings. It will eat through it. Be careful not to rub your eyes, face, clothing, etc. while you're working on the station, especially if you've touched the battery. If you're not sure where something goes or you are unsure how to use a piece of equipment, then you need to stop, get one of the lab staff, and have us assist you. This is very important because we'll be using scan tools in this lab, and we'll be testing sensors, and it's going to get just a little more hands-on-y and in-depth than what you're most used to up to this point. So if you're not sure, stop and get help. We will help you. So what we're dealing with in this case is gauges, gauge cluster systems. What do you know? So as I have written in my paperwork, the idea is, do you know if you're going the correct speed? Do you know if your car's overheating? Do you know if you're losing oil pressure? This is what the gauge system does. Essentially, its purpose is, gives information to the driver, or the operator of the motor vehicle, if you wish. So the whole purpose of the gauge cluster system is to tell you, the driver, or the operator of the vehicle, what's happening. How fast am I going? How slow am I going? Is the car overheating? Is there any problems? And the whole purpose behind it is to give you information. So what we're going to do is we're going to jump into about how does it give us that information. So the instrumentation system breaks down into 2 major categories. You'll have gauges and sending units. Sending units are typically called sensors. The gauges convey the information to you, such as speedometer or coolant temperature gauges, and are typically housed in front of the driver. It's that gauge cluster, that thing that sits in front of you in the steering wheel. Sensors physically measure information, such as vehicle speed sensors or coolant temperature sensors. Essentially, guys, in a nutshell, sensors directly measure the data on the vehicle, then they send that information to the gauges, which translates that electrical signal into a picture that you recognize. All right, so I have here on the picture, sitting right here on the board, I said take a gander at the temperature gauge on the left and the temperature sensor on the right. If I told you we had 4.8 volts of coolant temperature, it wouldn't mean much to you unless you're a pretty seasoned technician at Diag. But if you look at the gauge, you immediately know the temperature is below 100 degrees Fahrenheit. So essentially what the sensor is doing is measuring the temperature. It outputs an electrical signal that comes into the gauge, which translates the information into words, pictures, or any type of visual representation that you as a human being will recognize. One measures, the other reports. It's that simple. It really, really is that easy. I'm not going to hammer that to death. We'll just shoot on here. There we go. So virtually all the gauges you'll run across in an automobile are what they call fixed magnet style gauges. So the idea is the magnet inside the gauge housing are energized by a power input, usually 5 or 12 volts, and they move a gauge needle according to the information they receive from the sensor. I'm going to show you something on screen here real quick about how the magnetic device works to move the needle on the gauge face. So we're going to jump into this real quick. So what we've got on screen is a voltage gauge, and we have it cut away so you can see inside here we have a little gauge motor, and this is what we're going to send current through to get the needle to move on the gauge face. So as it gets various amounts of voltage, it's going to change the gauge face, which is how the motor operates. And we have it pulled apart here. You can see the windings inside of it. Works sort of like an alternator, whereas you send power through one of the windings through these connectors here. You're going to get the needle to move either to the left or the right, and the more voltage we send through one side versus the other, the more it's going to sweep. So we have it set up here to show you when we send power through the power probe. Notice how it goes one direction, and as it gets more power, it swings all the way. As we reverse the leads, we can get it to swing the opposite direction. And that's basically it. Those windings are just pulling a magnet left and right across the gauge, and as more or less power goes through it, you're going to get the needle to move a certain point. Yeah, pretty interesting, huh? So what we had there was a standalone gauge, but many modern gauge systems group all of them together in clusters. So we have a gauge cluster. The cluster houses all the gauges and connects them with a thin metallic film called a printed circuit board. In this type of gauge system, if one of the gauges goes bad, you typically need to replace the entire cluster. Though be aware that some systems do have those standalone gauges that I just showed you. So this is really, really common. This is going to be like your most common kind of setup. So when we take the gauge cluster that sits in front of you and we turn it around, this is what it looks like on the back. So this is a grouped together cluster. We cannot remove each one of these gauges. They're just housed permanently inside the plastic housing. And this printed circuit board on the back is what's going to feed all the sensor information into the gauges. It's also going to be the power supply to get those magnetic needles moving to get them to work. Also, as a side note, be aware that like each of these like printed circuit board lines, like here and here, these can break, they can tear, they can get dirty. So when you actually have a failed cluster, that's what we mean when we say the printed circuit board is bad. So it's really that simple. So we're just going to jump right in. Sensors themselves. So the most common type of sensor that we're going to find in an instrumentation system is called the variable resistance sensor, which means the internal resistance of the sensor changes as certain things act upon it. So the idea is that sensors change resistance. So we pump voltage into them and their resistance changes based on different things. So I have written down, I said sensors that change with temperature, such as the coolant temperature sensor, we call thermistors. Thermistors are sensors that will change their resistance up or down based on what temperature they detect. Sensors that change with pressure, like an oil pressure sensor, we simply call pressure sensors. Pressure sensors can't measure temperature. They don't change resistance with temperature up and down, but they will change internal resistance as you exert pressure on them. So, you push on them, increase or decrease sensor resistance. And sensors that change with movement, such as a fuel level sensor, we call potentiometers. All right, so you got three major styles. You got thermistors, press sensors, and last but not least, and if you feel like you're from Boston, you can call them potentiometers. So we got thermistors, pressure sensors, and potentiometers. Thermistors change with heat. Pressure sensors change with, you guessed it, I knew you were a smart cookie, with pressure. And potentiometers change with movement, right? So these are your three major kinds. There are more, but we're not going to hammer these to death. So just be aware that different sensors have different engineering technical terms, but the thing that changes in the sensor is resistance. The thing that classifies a sensor is what causes that resistance to change. So we got different sensors for different applications exactly for that reason. So let's slap those two babies together and show you exactly how they work. Just to give you a visual analog, if you wish, this is going to be an oil pressure sensor. This is a device that changes resistance with pressure. And this is an engine coolant temp sensor. So this is a device that's going to change its resistance based on temperature. So those are visual analogs there. So slapping all the systems together, I should say the two gauges and the sensors, let's show you how they work. So this is the old school gauge system. This is how it used to be for the longest time. And what sets us apart is that the gauge and the sensor are both in the same circuit and they're in series with each other. So again, what we have with the old school gauge system is we have the gauges in series with the sensor. So we got a battery power here, we got the gauge, we got the sensor. It's a very pretty drawing, isn't it? I'm really very proud. It's much better than my normal ones. I hope you guys can see that I'm improving. My mom says it's really good. She puts it on her fridge. But anyways, we're going to draw a path through the gauge, through the sensor into the ground. That's the path it takes, right? Pretty simple series circuit. The sensor itself varies, of course, with resistance. So these are my theoretical made-up woo-wah numbers, so don't look at them too hard. Let's say it ranges from anywhere from 2 ohms to 200 ohms. Again, as the resistance of the sensor goes up or down, and it's going to go up or down in resistance depending on what kind of sensor it is. ECTs change with temperature. As the sensor goes up or down in resistance, the amount of amperage that flows through the circuit is going to change. So we could, flow anywhere from like 0.02 amps, to 2 amps, depending on what the resistance is, right? And the gauge goes, as I see so many amps, I know what to change the gauge face to. So the gauge and the sensor are a pair bond, is what they call it. Yeah, they're a bonded pair. So they are matched together so that at certain range of resistance, we get certain amount of amperage, which the gauge knows gives a certain amount of reading. It really is quite that simple. Nice and in series, sensor goes up and down, changes the amount of amperage that flows through the gauge, which gives us a different reading. I give you the example on your paper of the fuel level sensor. So it sits there in the tank and it's attached to a lever. And basically, as the lever moves up and down, it's going to change the resistance value of the level sensor itself. Since the gauges, we're still dealing with, a simple old school gauge system, they're in series, the amount of amperage that flows through this circuit is going to change, again, as the sensor changes its resistance. And in this case, a potentiometer, the sensor changes its resistance based on the location of the float. So as the fuel level goes down, the float goes down. I'm going to show you on screen with an actual one here. If we take a look that the sensor itself is moving up and down with the level, it's going to change the resistance. Resistance goes up, less amperage through, and then the gauge is going to read a certain level. As it goes down, resistance is going to change as well, so we're going to change the sensor. The question, of course, is always, well, does the resistance go up as the lever goes up, or does the resistance go down as the lever goes up? And the answer is, of course, it depends. It all depends. You'll notice that I'm not giving you a lot of really hard statistics, a lot of hard numbers in this because the range of the sensors is completely different depending on the car. Like some engine coolant temp sensors, as they get hotter, actually go down in resistance, and as they get colder, they go up. And on some vehicles, it's the exact opposite. So what type of sensor is it? I can't tell you. It depends on what vehicle you're going to work on. When you go into the Mitchell Protoman and you look up that information, they'll tell you the range of a sensor, and they'll tell you basically what's going to cause that to change. All you need to know right now is how the gauges are getting their information. Again, based on the resistance of a sensor, especially in the old school system where they're in series. So aside from just sensors, we also have what we call the idiot light system. You notice the quotes. They will also refer to this more kindly as the warning light system, not just the idiot light system. But you'll always hear it called an idiot light system. They really like it. So in this case, we don't actually have a gauge. All we have is a dash light. This is literally like the old school diagrams that I used to draw for you guys back in Station 1, where it's just a light bulb. Like, that's it. That's all it means. Warning light is just a light bulb. And in this case, I'm going to erase this real quick. We have circuits that go through the dash light, and then they go to a switch. So they just go to a switch. There is no sensor in an idiot light system. I'm going to show you on screen right here the picture of a dash that has a warning light on it. So there is no meter measurement for this, which should be the battery. We're showing you the battery right now. It's just a light. Either it comes on or it goes off. If the light comes on, it says, oh, there's not enough charge. If it goes off, it means, yeah, it's probably just fine. You can't tell me what the value of the charge is. You can't go, oh, the alternator is clearly putting out 15.5 volts because the meter says so. There is no meter. It's just a dash light, right? So back to our diagram. If you look, it's just a switch. And what kicks the switch shut depends on what type of switch it is. So if we have, let's say, a low oil light, right? So when oil pressure goes too low, we'll close the contacts, just like that. And then this will find a path to ground, which will cause the light to come on. And usually this light says low oil pressure. And as oil pressure goes back up, usually when you accelerate, those contacts break open, and it causes the light to go back off. And that's it. It's just an on or off. It's either warning, no warning. There is no intermediate steps. Gauges will gradually show you. You can watch. The oil pressure gets lower, it gets lower, it gets lower. You can see it get lower. And then it's too low. But a dash light system or an idiot light system is just going to boop. It's just going to kick over, and that's it. So I'm going to show you on screen exactly how the switching device works. Yeah, so there we go. So this would be something like a low oil pressure switch. So I said pressure sensor in here, but I was an idiot and I was wrong. We're just going to call this a low oil pressure switch. This is like our fancy cutaway of what it looks like. And if you take a look at the levels here, so we have oil comes up into the bottom, and then it applies a certain amount of pressure. So it lifts these contacts right here off of each other. And you can see I'm going to draw in green right there. See, they're not touching, right? the this entire system is going to force these contacts closer towards each other. So those contacts right there. As this area drops down, those contacts will touch. And this is all prearranged. This is pre-built from a factory, depending on what the switch is. So at, say, 10 pounds per square inch of oil pressure, those contacts will touch. Anything above it, so if you bump up to 11 or 12, they'll unseat the contacts. They won't touch anymore, and the light will go off. Again, because when this switch right here, when these contacts touch, this circuit is complete. And then we complete the circuit and the light comes on. That's it. That's all we have with a system like that. It's very, very simple. We've covered this kind of stuff in Station 1, as in series circuits and switching devices. You see kind of how easy it is to apply those Station 1 principles to everything else. It's all we've got. All right, so if it doesn't quite make sense, rewind the video, watch it again. I swear to God, it's very, very easy. And if it still doesn't make sense, what are you going to do? You got it. You're going to go ask for help because you're a go-getter. I know you can do it. And last but not least comes, as I call it, the new hotness, which is the networked instrument cluster. So there's a lot of information here that we're going to jump into real quick. I mentioned on your paperwork that modern vehicles, you're talking 2009 and up, are equipped with anywhere from 10 to 25 different computers, which we call control modules. So each major system on the vehicle typically has its own module. For example, body control module, air conditioning module, power window module, powertrain control module, transmission module, etc. If there's a thing on a car, you can believe that there is a dedicated computer to assisting that process. So the various modules control different sections of the vehicle, and they trade information with each other across the self-contained network inside the car that we call the closed area network, or the CAN. So if you ever hear the CAN system, it's literally the internet in your car, which we would call an intranet, because at the moment it would be self-contained in your car. Just like the internet is literally your computer and the computer of your friend, and the in-between spot is, of course, 4chan, because you're all respectable human beings and all use 4chan like gentlemen and ladies and anything in between, right? So all three of those things are networked together and share data across. The same thing happens inside the car. You know, you're going to have various modules talk to each other. So what we get to do in a modern gauge system is we can use the CAN to communicate between the gauges and the sensor. So I show you on the picture. So in the picture, the powertrain control module receives information from the sensor itself, then sends that information over the communication wire, which we call the CAN bus. The CAN wires are going to be the CAN bus, which is these over right there. And it sends that information to the instrument panel control module. And the instrument module sends that information to the gauge itself. So again, the sensor is connected to a powertrain control module here. So unlike the old school gauge system, they are not connected in series. The sensor and the gauges are separate from each other. They're in parallel, if you will, so they don't tie into one another. So the sensor itself, let's say this is the ECT sensor. So this will be your engine, coolant, temp sensor. You're getting real used to these acronyms, I hope, just very quickly, because you'll hear endless amounts of acronyms as you work in the field. So the engine coolant temp sensor is, of course, attached to the powertrain control module. Pro tip, because the powertrain control module, which controls the engine itself, needs to know what engine temperature is, because the hotter an engine is, it needs to change when we fire the spark plugs and when we fire the injectors and how long we keep the injectors open, right? So that information is germane or pertinent or applicable to the powertrain, because we need that for the engine. So we already get that information and send it to the control module for the engine. So it goes, hey, who else could use this information? Well, the instrument control module could use it, because we have an engine coolant temperature gauge inside the car on the dash. So it takes that information that it already has, sends it across these two wires. So the CAN bus wires are always two wires. I'm going to show you on screen here real quick. They're these like fun little twisted pairs. The pairs are twisted, FYI, to cut down on radio interference. You'll notice they're really thin. Too much radio interference, which we call electromagnetic interference, will cause that data to be corrupted and be wrong. So we twist them to cut down on that. So it sends that information from the powertrain control module through those twisted wires all the way to the instrument control module. The instrument control module goes, hey, I got information that tells me what the engine temperature is. Sends it straight down to the gauge. The gauge itself reads on the gauge face right in front of you and goes, here's what the temperature is. That's it. That's what the modern hotness is. If you have a modern gauge cluster, this is how it works. It's all networked together. No more in-series kind of systems. It's just information comes from various sensors monitored by other modules that get sent over the closed area network to the control module for the instrument cluster. So sensors get picked up, get sent back to whatever their respective modules are. That module transmits that data to the instrument control module, sends it to the gauge, and then the gauge reads out accordingly. It's all separate. So the purpose of the CAN system is it reduces the total number of wires on the vehicle. This actually, it seems more complex, and in setup it is, but it cuts down on the sheer number of wires. Because as I showed you before, the CAN wires are just 2 wires. They're 2 small twisted pair wires. That's it. That's all I need to connect all the modules between the car. And if I put my modules really close to their respective sensors, like if I put the powertrain control module inside the engine bay, I can run very few wires to each of the sensors. And then to communicate all that information to the rest of the car, I just need 2 CAN wires. That's it. That cuts down on wiring immensely. It also cuts down on wiring problems, because now I don't have a boatload of wires running all the way through the chassis of the vehicle. It's just 2, and we know exactly where they are, and they're easy to find. So this cuts down on wiring, which cuts down on weight, which cuts down on complexity, but it does run more complex systems. So like, you as a technician now need to understand how this new system works, and it's going to change the way you diagnose certain things, all right? And technically, we do have more things that can go bad. In the old school setup, boop, boop, boop. Back we go. I have a sensor, I have a gauge, and then I have all the respective wires that connect all of them, right? So that's 1, 2, at best 3 things. So if we jump back, I've got a sensor, I've got a powertrain control module, I have CAN wires, I have an instrument control module, and then I have the gauges. And of course, I have all the wires that connect all these things together. That's more systems. That's at least twice as many things to go wrong, right? So it seems. The beauty is the powertrain control module and the instrument control module are generally very stable. Like most computers, they don't break very often, right? So there is more things to go wrong, but they tend not to, because they tend to be more reliable. So realize it's both a more complex and simpler system. It's like, Schrodinger's like system. It's both complex and not complex, depending on how you look at it. So be aware that this is how the system works. Again, if you aren't sure, go back, watch again, and if it still doesn't make sense, come get help. We will explain it to you. It's very important for you to understand how the new hotness works, because it is everywhere. It's hot. Everybody wants it, right? The time has come. Oh, lo, how the time has come for the favorite diagnostic time. It's diagnostic time. It's diagnostic time. It's my favorite. So we're going to start getting into diagnosis, and I'm going to show you how to diagnose gauges on a vehicle. Just like anything else. This will be using our 2018 Honda Civics. I'm so proud. They're so pretty. I bet they're sitting right in front of you right now. You can look at them, touch it and tell you love it, because it took a lot to get it to you. It's proud to be near you, just like I am right now in your ear talking to you. Anyways, since this is incredibly weird, we're going to go on to diagnostics. So sometimes gauges fail to work, sometimes they report inaccurate information, like reading 100 degrees Fahrenheit when the engine is clearly too hot to touch and it will burn you. And when that happens, we got a couple things that go wrong. So here's from the most to least likely problem in a vehicle for your diagnosis. 1, the sensor itself is bad. 2, wiring to the sensor is bad. 3, the gauge or instrument cluster is bad. 4, the wiring to the gauge and instrument cluster is bad. 5, there is a communication problem with the closed area network system if you're dealing with a new hotness. Or 6, one of the modules themselves are bad. That's it. That's your 6 trouble spots to diagnose any gauge problem. That's it. It's really that easy. And you'll probably never deal with anything in 5 and 6. It's very rare for a communication problem to exist, and one of the modules typically does not go bad. So you got sensor problem, wiring problems, 2 the sensors and 2 the gauges. Like, that's it. That's really the heaviest part. So as we go forward, I'm going to show you how to diagnose steps 1 through 5. I'm not going to show you how to do 6, because it's a whole different complex thing to diagnose a computer, and you guys as new technicians don't need to know that. So as we move forward, realize we're tackling these 5 and knocking them down and beating that guy out of them. So you've been listening to me talk a lot, so buckle up. We're going to show you how to do these on the actual, I'm going to show you on the board first, I'm going to show you through lecture, and then I promise, I swear to God, I'm going to let you diagnose your own problems for practice. I'm going to put the scan tool in your hot little hands, and you're going to diagnose yourself. You just have to stick with me for just a little bit. We'll get through the lecture part. I swear it's worth it. We have to do this first. Step 1, you guys should remember this from every other station you took before this, because of course, you took other stations before this, right? At least station 1. So number one step is verify the customer's complaint. You can't fix a problem if you don't verify that it's even there. So always verify that the customer's problem exists before doing anything else. Always verify. Please, for the love of God, verify the problem. If the customer says their coolant temperature gauge doesn't work, you need to get in the vehicle, get it to operating temperature, and verify if it works or not. Okay? Because sometimes customers don't know. They don't know if a thing is supposed to be like that. They'll say it's a complaint, but it's pretty normal, right? Every time I pull the trigger of the gun, it's really loud. Well, ma'am, it's supposed to be that way. Is it? I had no idea. Always verify the customer's complaint. Don't just take their word. Always verify. Once you've confirmed the problem exists, you need to perform a visual inspection. So if a speedometer doesn't work, you need to crawl into the car. You need to inspect the sensors themselves. If the engine coolant temp sensor gauge doesn't work, you need to inspect the ECT sensor. Check the sensors or gauges for loose connections, broken wires, or physical damage, right? So you need to get under there or get in there and look at these things. A good visual inspection can save you the embarrassment of wasting precious hours diagnosing something such as a loose connector. So be aware. You're looking for cut wires. What are you looking for in inspection, right? Loose wires, bad connections, and 3, we're gonna keep this PG as heck. We're just gonna say stuff. Weird stuff, right? Look for loose wires, look for bad connections, look for weird stuff, right? This is a mouse chewing through something, there's a burn mark, someone dropped a cigarette lighter onto the actual sensor itself. You would be stunned by the things you can see with your eyeballs and or touch with your hands. Do not skip the visual inspection, very, very important. Don't do it, you'll find a lot of stuff. Even if you're not used to doing a visual inspection or you don't know what's normal, visual inspections will help you see what is normal. You will also most likely be working with other technicians whom you can call over and go, does that look weird, Mark? And, he'll chew and he'll look at you like you're crazy. Go, I ain't supposed to look like that. That's what he's going to say because Mark is a rough guy. He's been having a hard time. His wife doesn't come home at the right times, and, he's had a good time in Vegas. So, he's going to be like that. Either way, don't be afraid to ask. They'll come over and help you. Even Mark will come over and help you with visual inspection. Step 2, you're going to hook up a scan tool and you're going to check for trouble codes. All right? It's very important. On modern cars, almost every sensor that feeds information to the gauges also feeds information to the engine transmission control modules to make sure the vehicle runs and shifts correctly. Okay? This means that if there's an issue with certain sensors or their wiring, the modules will typically throw a diagnostic trouble code, so DTCs, diagnostic trouble code. You will see this a lot. This is informing the technician that it's not receiving the correct or any information, all right? So I've written on the board DTC. So you guys will typically know a diagnostic trouble code is a check engine light. So that's the fastest way to convey what it is when that check engine light comes on the dash. Note very quickly that you can have diagnostic trouble codes and the dash light will stay off. Okay, so just because there is no check engine light does not mean there are no DTCs. But the big purpose of this is to help guide us. If we pull a DTC, it's gonna help point us in the right direction. So again, I say let's say a customer complains an ECT gauge doesn't work. You hop in, you verify it doesn't work, and your visual inspection shows no problems. So you run the DTC check with your scan tool, you find a code that says ETC sensor out of range, which informs you that the module isn't getting the correct information from the sensor, either due to the fact that the sensor is bad, it's disconnected, there's bad wiring, etc. The DTC acts like a compass that guides you in the direction of the sensor. DTCs act as a compass to the problem. They are not your final step in diagnostics. If it says, well, there's a problem with the ETC sensor, I swear to God, if you pull up a DTC for an ECT problem, and you just replace the coolant temperature sensor because you said, well, the scan tool said it was bad, I'm going to lose my mind. I'm going to lose it. I'm going to roll around on the floor and I'm going to scream like a banshee. It's going to be nuts. And then I'm going to make sure like the ghost of every dead scan tool of the past haunts you forever for being just a really lazy, junky technician. That is not what the DTC is telling you. It says there's a problem with the ECT circuit. Is it the sensor? Is it the wiring? Is it the module? It's pointing you in the direction. That way you're not checking the wheel speed sensor or checking the fuel level sensor. You have an ECT problem. So the big thing and the big reason we take the DTCs is there are so many sensors and so many weird problems that could pop up in this car. We need the scan tool to help weed out potential problems and speed up our diagnosis. It's a great compass. It is not a final leg of diagnostic.
So our next step, step 3, is going to be inspect and test the sensor itself. So as we walk through in diagnostic steps, we've pointed out that the scanner is not enough to completely condemn this problem. So we need to test the sensor with the DVOM to 100% ensure we don't have any issues. So first things first, I'm going to pull up a YN diagram for the ECT sensor number 1, which is what we're going to be testing here. The ECT number 1 has 2 wires that go into it, a purple wire with a blue tracer, and then a purple wire with a gray tracer. The purple wire with the blue tracer is going to be voltage from the PCM, which is right here, and then the purple with a gray wire is going to be the ground connection. I'll show you later how I figured this out. I'll show you how to find it in Protoman, but for now, keep in mind that the blue tracer wire is voltage in, and then the gray tracer wire is ground wire out. With my DVOM hooked up with the black wire to ground and the red wire touching the purple wire with the blue tracer, I should see between 0.6 volts and 3.5 volts on this wire, because what the PCM is doing is it's sending out voltage that will vary based on the resistance of the engine coolant temperature sensor. As the ECT changes temperature up or down, the amount of voltage sent out by the PCM is going to change. So when we test this wire, we want to make sure that we're between 0.6 volts and 3.5 volts with the key on and the engine running. What you'll typically find is that the voltage will drop as the engine gets warmer. Conversely, if you hook up your DVOM this way and you get between 0 volts and 0.5 volts, then you have yourself a bad reading. What this typically indicates is that from here to here on this wire, there's going to be an open or way too much resistance. This is doubly true if you're reading about 0 volts, because if we cut this wire in half, we're going to get no voltage reading to that ECT sensor number 1. So if you're reading 0 to 0.5 volts, it means too much resistance or an open in this wire. Next up is checking the ground side. Remember, we're doing a voltage drop on the ground side because we're testing ground to ground. So I have my black lead on my DVOM connected to ground, and then I have my red lead on my DVOM attached to the purple wire with a gray stripe down it. And what we're doing is we're voltage drop testing the ground. As we've talked about multiple times before, you should be getting between 0 millivolts and 200 millivolts drop if the wire is good. That means it's a good reading. Anything under 200 millivolts on a ground-to-ground voltage drop means that we have a good reading on the ground side. Conversely, if you read above 200 millivolts, so say 300 millivolts to 1200 millivolts, which is about 12 volts, when you're testing the voltage drop on the ground side, this is a bad reading. You should not get between 300 millivolts to 1200 millivolts. This means that between here and here, so between the connector at ECT sensor 1 and this whole wire all the way to the ground connection, that means there's too much resistance, or there's a break or an open in the wire. So if you get the reading 300 millivolts to 1200 millivolts, that means the ground side is bad and you have some type of break or resistance in that long wire.
So part C, the third part. If the sensor has good power and a good ground, the only thing left to do is replace the sensor. That's it. That's it. You should see a pattern from the same stations that you've done before this. Good power, good ground. The only thing that's left is the component. So get rid of the component. All right? It's a big pattern. I put the fine print at the bottom. Okay? This final part of replace the sensor only applies if you know the gauges are good first. So do not replace the sensor without checking the gauges as well. It is possible for there to be a good sensor with proper power and ground, yet the sensor won't detect anything if the PCM is bad. This is very rare, but it does occasionally happen. So for the sake of brevity, which is to say to keep it short, I do not go into how to diagnose specific ECU problems here. We'll do that in a later class. But know that the method I just taught you is effective. It's just not 100% foolproof effective. Okay? Sensors can have good power, good ground, and the sensor itself can work, and the module can be fritzy. That is shockingly rare, and there are ways to detect this, but I will not teach them to you, okay? Because we only have so much time, and your life is only so short. We'll cover that at a later time. But know that the three-step process I'm giving you works. Also, do not condemn the sensor until we check the gauges, which I'm going to show you here real quick. Check the power, check the ground. If power and ground are good, Don't go replacing the sensor until you're 100% sure that the actual gauge cluster isn't working either, which we'll show you right quick. So here we go. So step 4 is checking the gauges of the instrument cluster. Okay, so if the sensor checks out as good, or we've done the power and ground check and we're waiting to condemn the sensor, we'd have to check the gauges itself. These break into 2 systems, all right? Again, instrument clusters and individual gauges themselves. Okay, what you will see more often than not is instrument clusters, super common. I'm going to make a number up right now, like 90%. This is going to be 10%, but I'm going to show you how to do both just in case, depending on what you run across, all right? So be aware. We're going to start with the most common and the easiest one first. So A, checking the instrument clusters. So with most modern vehicles, again, 2009 and up, the gauges are installed in a cluster. And when you turn the vehicle on, they go through what's called a gauge sweep, which is when the gauge needles sweep across the entire face of the gauge, then return to their resting system. This is a system self-test. It makes diagnosing them extremely easy. If a gauge fails to sweep all the way across and back, then the gauge itself is faulty. Pretty simple, yeah? So I'm going to show you on screen. Here's the vehicle going through its gauge sweep. So turn the key. There go the needles, and the needles back. All right? So I'm going to do it again. Here we go. Needles go, needles come back. If you watch, if you want to rewind it, could be my guest, watch that all the gauges sweep all the way across, and then they sweep back. Okay? So if all the gauges in the entire dash fail to light up and go through the sweep, you're most likely dealing with a broken fuse that powers the cluster. Or if there's a break in excessive resistance in the power and ground wire to the cluster, and you'll need to diagnose that. Because we know how to check power, right? We know how to check ground. I'm not going to show you that explicitly here again. We only have so much time to live and breathe. But you should know how to check power going into the cluster. Check the power wire. You're going to need a wiring diagram. And you should know how to check the ground. Do the voltage drop across the ground. Okay? Again, using our diagnostic principles. If the whole gauge fails to light up, there's either a problem with the gauge cluster itself, or it's a problem with the power or ground. It's not a failure of one of them. So depending on the cluster design, you'll need to remove the cluster and replace non-functioning gauges if an individual gauge doesn't work. In some cases, the whole thing will have to go. All right? So if one gauge fails to work, so like we do the sweep, whoop, whoop, and like, you know, the ECT gauge fails to sweep to the right and sweep to the left, it just freezes out. Depending on its design, we're going to flip it back, and you will see if that gauge can be replaced. Most of the time, it can't. If one gauge in an integrated cluster fails, the whole cluster goes, which means you have to replace the whole thing. You can't just replace one. An individual gauge can be replaced. It depends on the vehicle, which is why it's hard for me to make universal statements right now. But know that the gauge sweep is super important, and it too is very easy to diagnose. And the fun part is you can also use your scan tool to pull up codes for the instrument cluster. So if the instrument cluster fails to go through a gauge sweep, we can still plug in a scan tool and check for diagnostic trouble codes. Maybe there's something there that we don't see. But the cluster is pretty easy to diagnose compared to anything else. So I'm going to write my steps out real quick. Again, review. Gauges should sweep. One gauge does not sweep, then gauge is bad. Simple enough. All gauges fail to sweep. Either no power, bad ground, or bad cluster. Caveat, as always, could be a bad module. It's unlikely, but it could be. That's it. Pretty simple, right? Gauges should sweep. If one gauge does not sweep, then that gauge is bad. If it can be replaced, replace it. If it can't, replace the whole cluster. If all gauges fail to sweep, you either have no power, you have a bad ground, or you have a bad cluster, the module's bad. Easy. Boop, boop. You're getting, I really hope this is appearing as simple as it hopefully should be. It's really not that complicated. Checking individual gauges is shockingly easy if you have standalone gauge systems. Mine is actually the slightly more complicated version. It's still very easy. It'll have a 12 volt input, boop, boop, right there. It's going to have a ground. And what are you going to do? You're going to check for voltage input, and you're going to check for ground, just like everything else. A more complicated gauge system may also have an input signal from the sensor itself. So the 12 volts in and the ground out is designed to move the magnets inside the gauge so that the needle can sweep. And then there'll be a third wire that comes in most of the time, which will then tell the gauge which position it should sit in, okay? That's going to be the more quote-unquote complicated one. The simple system is going to get rid of that entirely, and all you will actually have is you'll have a 12 volt input, and you'll have a ground. And depending on what the sensor voltage is, it'll send 1 volt to 12 volts into the actual meter itself. And then that'll change where the position is at. So the computer will vary the amount of voltage that goes to that actual gauge to change it, and then of course it'll just ground out. That's it. That's all that it is. Check to see that the voltage that goes in is correct, depending on what the range is. You will find the range using service information, and of course, check the ground. It's that easy. It's beautiful. Powers and grounds everywhere. Like Dance of the Sugar Plum Fairies, you can see them all dancing in unison, and then the Rat King comes, and you got to diagnose him away, right? My analogies are just on point like crazy today. Thank you for sticking with me. So I hope you see that how easy a lot of this is, and if it's not, go back and watch and listen to my inane voice cover this 1,000 times. And since you have been so wonderfully patient, what I'm going to do now is we're going to go out to the car, and you, alongside me, are going to diagnose, I believe, 2 or 3 problems on the car itself. So I'm going to show you with these example work orders. We're going to go through it, but here's the fun part, right? Thank you for sticking with me. Now let's go have some fun diagnosing this stuff in the real world. So before continuing into this section, you need to go to the front desk. You need to check out the scan tool and the DVOM because you're going to need both of these tools for the hands-on bug testing that we're going to do. So go grab those, and then we'll jump into this repair order real quick. All right, so for our first bug, we're going to jump into the work order for this. So you got repair order number 1. At the top, we're going to look at the customer complaint. My engine temperature gauge doesn't work correctly. That's what the customer's concern is. Our job, as always, is to verify the problem exists, and if so, figure out and explain why. So to verify this complaint, we're going to have to check to see, does the engine temperature gauge work correctly, yes or no, and then we're going to analyze our symptoms and go from there. I give you kind of a preempt that says, well, what could cause it? Bad sensors, bad gauges, ECU failure, all the above. In case you are unaware, it should be all the above. So before we actually go in and start a visual inspection, I'm going to show you how to pull up the wiring diagram for the ECT, and then I'm going to explain how the ECT works. That way you kind of have an overview before you can start to diagnose. So let's jump into that. Okay, so this is how we're going to access the pro demand so we can get to the wiring diagrams. If this is obviously not your first station, you have been through this song and dance before, but here we go again. You're going to find this icon on your desktop, pro demand automotive repair, double click with the left, it should bring it up. It should log you in and should bring you to, of course, the home page. I'm going to close that real quick. There we go. So the home page should be here, and then we need to select a vehicle. Vehicle selection, of course, is going to be our Honda Civic. So we're going to have the 2016. And scroll down to Honda. We're going to pull up the Civic. We got a 2-liter engine on this one because we're not quite fancy enough for the 1.5. We got the EX model. It's going to automatically fill in the transmission for you, and then we're going to say use this vehicle. So as is always, we're going to go into the search bar up at the top, and I'm just going to type in ECT, engine coolant temp sensor. That's basically what it is. We're going to click on the hourglass or press enter, and it should bring up ECT inlet sensor. So we're going to click on this right there. And again, we have multiple options: component locators, parts and labor, wiring diagrams. What we want is the wiring diagrams because I'm going to walk you through how it works. So it's going to bring up wiring diagrams for the engine coolant temp sensor for the 2-liter engine. Now we have engine performance circuit. There are 7 pages, 1 of 7. This is going to have almost all the engine control sensors on it, so there's a lot of pages. And if you look, as we look here, we got the underhood fuse relay box, we got, the PCM, left side of the compartment, APP sensor, we got FTP sensor, secondary HO2S sensor. Be aware that you guys will be informed of what this is in 126, so don't sweat it. And what we're going to do in this case is we're going to go all the way down to page 7. Because I've already scoped this out, and that means I know exactly what I'm doing. So I tell you. So we go all the way down. Engine performance, 5 of 7, 6 of 7. You know what? Yep. There we go. So engine performance circuit, 7 of 7. All we're going to do is left click on this picture. It should bring it up for us. Again, we have the sliders on the left. That's going to allow us to zoom in and zoom out. So we left click and move those. I'm going to zoom in just a little bit. I'm going to click my little push icon here, left click, and you can drag. And there's my ECT sensor. So it says it's on the rear of the cylinder head, which is where we're going to find it. And it has two wires that go into it. It has a purple and blue wire, left click it. And then it has a purple gray wire. So purple with blue means that the wire itself is purple, and the second color means that the tracer, like the thin colored line that's on it, is going to be blue. So the whole wire is purple, and then it has a thin blue line that goes down it. Purple with gray means it's entire solid wire of purple and has a thin gray line that goes down to it. So that's what we mean by solid color and tracer. So the first is the actual solid color, the second is the tracer color. So if we look at where the wires are coming from, we have the PCM. It's going to feed into the ECT, which is right there. And just as we had mentioned before earlier in the station,
it's going to send out between 0.6 volts and 3.5 volts, depending on what the resistance is of that ECT sensor number 1. So as the engine coolant temperature changes, gets hotter or gets colder, that wire, that purple with blue wire that feeds it, is going to vary in voltage, but you should get between 0.6 and 3.5.
Where it's going to go, we need to find out. I'm going to show you that it goes to a ground, but I'm going to show you how to trace this all the way back to a ground. So when we read these diagrams, we're on page 7 of 7. If we want to find where this wire goes exactly, we need to follow it. So we're going to follow it all the way down, and if you look on the left side of the screen, we have 1, 2, 3, 4, 5, and 6. What these numbers on the left side denote is where this wire comes out on the next page. So I'm going to give you an example. So pay attention. We got purple and gray wire, and it goes to number 4. So I'm going to close this X right there. I'm going to scroll up to number 6 of 7. All right, so if you look on the right side of page 6 of 7, we have 1, 2, 3, 4. Notice how it's my purple and gray wire. That's the same one from the previous diagram right here. So it went into 4, and it comes out at 4. So let's keep following this all the way back. So if we follow it all the way across, it goes to the left side of the screen, it goes to 4. So we scroll up, we find number 4. There it is. We're going to follow it again. Now keep your eyes on it. It's going to go all the way down to a block. So let's go ahead and left click this. Let's zoom in. And since it can be a little hard to trace these wires, we're going to click on it. And now it's going to highlight for us. This way it's much easier for us to follow. So we go all the way down. Whoops. Yeah, there we go. Click the hand. Down, 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 down. There it is. Okay. And it goes to this giant block that's on the back of the engine. So this is what's called the terminating block. So what this is a giant ground where all these wires ground out at. So that's where the ECT sensor gets its ground, is on this junction JC C004. So if we want to find this wire and trace it, we know where it's at. But the big takeaway I was looking for here is to show you how to follow wires all the way across multiple pages, because you're going to have the numbers on the right side and you get the numbers on the left side. So if you match right to left across pages, you can trace these wires back. But that's how you're going to have your wiring diagram for the ECT. All right, so that's what we're going to have. Now I'm going to go into the visual inspection. I'm going to show you how to start this. Okay, for starters, we're going to have to actually set the bug. So you're going to come over to your bug panel 1, 2, 3, 4. You're going to switch it down. That should put the ECT bug in place. So with your keys, you're going to hop into the car, and we're going to verify the customer's complaint. Let's see if we do actually have an ECT problem. So go ahead and put the key in. You can turn the key all the way, and you can start the car. Make sure the engine turns on. Our gauges come up, and our temp gauge is on the far left. For starters, 1, you will see a check engine light is on. You will also see that the ECT gauge reads full hot. So it should read somewhere around cold, or at least in the middle. And this is a default for a failure in the ECT to read full hot. So what we're going to do is we're going to hop out, and now we're going to do our visual inspection. So we're going to check, and we're going to make sure that there aren't any serious problems. We have a wiring connector here that basically gives an extension on where the ECT is at. So I'm going to show you here all the way nestled down where it's at. So this is why we have the extension on it, because it's really hard to get to this thing. It really is. So if I can find a good angle on this thing here, looking, and there it is, that blue connector in the back. So again, there's our wires with the tracer on them, and we put the extensions out just so that you guys can be able to test a little bit easier on this one. Now before continuing, I'm going to have you go turn off the engine. So make sure the engine's off before we continue. So with the engine off, now what we're going to do is we're going to double check the battery. Going to make sure that's good, because we're going to make sure the battery's pretty solid before we go making any kind of sensor diagnosis problems. So again, you're going to hook negative to negative. You're going to touch positive to positive, all the voltmeters on the voltage scale, and we should see at least above 12.6, which I certainly have here. So what we're turning to next is going to be the scan tool. So you should have the scanner you checked out, and you should have the scan module. The scanner itself should be on. If it's not, then you're going to go ahead and hit the power button to turn it on. So go ahead and hit it. You should click on. You should see it boot up with the snap-on symbol just like this. And it'll take a few minutes because it's a little slow, but it'll get there. While it's turning on, we're going to turn and we're going to take our scan module, we're going to pick it up, and we're going to go plug it in. So this is wireless, so it connects through Bluetooth, so we don't have to have it connected physically to the scan module. So we'll pop open the door. I'm going to show you where the data link connector, the DLC, is at. It's down underneath here, and you should see it, this little white connector right there. And we're going to take the scan module connector, and it's got the little silver tang. Silver tang should point towards the passenger side since it is a unidirectional connector. It should just plug right in. Once it seats and it plugs, it should turn green. We're going to take a look at the actual scan connector itself. It should turn green as well, which means that we're good to go and it's ready to communicate. So we need to keep this out of the way of our feet so we're not stepping on it, ripping the cord out. So I like to pick mine up. I like to set it right here in the cup holder. Keeps it nice and safe. No serious problems with it being right there. Nice and dandy. So we're going to get the connector connected, and to do this we need the key in the ignition. It needs to be in the run position. Do not start the engine, just make it sure it's in run. We should get the gauges to sweep up like this. Make sure we have our scan module out of the way. Don't be kicking the cords, don't be stepping on it. You should have your scanner booted up to this home screen. Yay if so. In this case, we're just going to select the scanner option. That's going to bring us in to selecting our vehicle. Sometimes it's a smidge finicky. Make sure you get a good press on it, otherwise it's not going to read. This ain't an iPhone, I'll tell you that much. So once the scanner kicks in, it's going to initialize and start trying to communicate, and then we're going to have to input the model and vehicle information into the scanner so it knows exactly what kind of protocols to follow. In this case, we need to select the make, which of course is going to be a Honda, so you're going to pick Honda from the list. And then it's going to give us two options. It's going to have automatic identification and manual. We want the manual just to make sure we get it right. So we're going to ID this as a 2016 vehicle, even though it is technically 2018. And we're going to select a Civic. So we got Honda Civic 2016. We have a 2-liter engine. And then we're going to hit OK. Beautiful. So now what we have here is a bunch of options of which sections to go to, but we're just going to select code scan, and we're going to code scan all the modules on the vehicle. You see the list right there? That's how much it's going to scan. We're going to hit continue. We're going to make sure the key is on and the engine is off. So you got the gauges on, engine is not running, so you're set. So go ahead and hit continue. It's going to scan all the modules. Trust me, it's going to take a bit of time to get through all of it. There's a lot to scan. You might be sitting here for a minute or two, and you're going to see stuff pop up, for example, on the screen right here, ECT sensor already. So we can already see the codes as they come along and come alive for us. So with the code scan done, we're going to check our two engine codes here, both of which are P powertrain codes for the ECT sensor. So the circuit input is too high, which is pointing us to a potential ECT sensor problem, probably with one of the powers in or the ground's out. So this is sort of like our compass pointing us in the direction that this isn't a gauge problem, it's probably a sensor problem. So if we're pointing us in the right direction, now we can actually hop out and we can go physically test the sensor for input and ground. Yeah, hop out, go ahead and head all the way over to the car, and you should have your DVOM that you've already had checked out, which we'll be using to double check the input on the sensor. And if you remember from the diagram I'm showing you on screen, the blue one, it's purple with the blue tracer, is going to be the input. So the blue wire is going to be the one we're checking. So we're going to set here to voltage. We're going to connect the ground to the ground and slap it right there. And then we're going to take the power and we're going to check the blue one. So that's our blue tracer wire. Remember, ours is blue because we have an extension on it. And we're going to see if we get voltage into the system.
And we should be getting around that 0.6 to 3.5 volts because that's the input. So when I sit here and I test it, I'm taking a look at my DVOM, and I'm on millivolts right now. So I have like a 305 millivolts. I'm going to change it to regular volts. Yeah, I'm coming up with almost nothing. There's almost no voltage to that connector. That is no good right now. What this means is that the ECT sensor is not receiving proper voltage because I created an open in the circuit. See, I'm going to test again. Yeah, getting nothing but millivolts, so it's too low even when I switch the range to volts. See what happens when I turn the bug off. So flip the bug off. There we go. And you'll see 2.8. It's in spec with the bug. There's a big open. Too much resistance is in there. That's what's killing this system.
So with that knowledge, that means we know what the problem is. We're not getting enough input voltage in the sensor, which is throwing a code, which is causing the gauge to read incorrectly. So the customer's complaint, my engine temperature gauge doesn't work correctly. Did we verify the problem exists? Why, yes, we did. And did we figure out what the problem was? We did. So under cause of problem, this is what we're going to need to fill out now. It asks, what is the cause of the customer's complaint? Write a short paragraph, explain what caused the problem, back up your conclusion with evidence. So I'm going to show you the first part here, which we always write in simple English called layman's English, to just explain straight out what's the problem. What's the problem? There's no power going to the engine coolant temperature sensor, ECT. That's it. That's what's causing the problem. That's what causes the customer's complaint. Now, the second part, after the comma, is backing it up with data. So the idea is, like, how do we know this? Well, we performed a voltage check on the input wire, and we found no voltage. So what's the problem? No power going to the ECT sensor, which causes the gauge to read incorrectly. How do I know this? How can I explain this to the customer and my boss? I did a voltage check, boss, and there's no voltage going into the ECT sensor. So there's no reference voltage. That's it. That's what the problem is. So first part, layman's English explanation. Second part, back it up with evidence. Always got to do it. Explain in English, then back it up with evidence. The second part is correcting the problem, because if we know what the problem is, we should know how to correct it, which I have written out. We're going to have to trace the input wire to find any opens or resistance or repair or replace the damaged wire. In this case, there's an open because I bugged one in there, which is what the switch is doing. That's why I know there's an open in the circuit. The only other problem, if this was actually a real-world vehicle, would be that the computer itself is not sending out any reference voltage, which, truth be told, is a real doozy headache of a problem to solve, which is way too complicated for the purpose of this lab. So for right now, all I'm going to have you write out to correct the problem is I would have to trace the wire and find where the open's at. I am not having you physically trace the wire because it runs 1.5 miles underneath the bottom of this car. Trying to trace it down to the PCM is too hard for you guys. So for your repair, we're just going to trace it, find the resistance, and repair it. So that's what we're going to write out. So this should be how we complete and fill out a work order. I'm going to expect mostly the same when you do the test. Again, you got to tell me what the problem is when you test out in perfect layman's English, and then back it up with evidence. Why should I believe you? You can't just say, it's bad, Skylar. Well, yeah, you can tell me that, but I need to know why. How do you know that? Make sure you always back up what you got with evidence, and you'll always have a great work order on your hands. With that all out of the way, we're going to start breaking this down, and I'm going to show you how to reset the code. So we're going to pull the bug out of the system, make sure the bug is off, flip that switch up, and I'm going to show you how to use the scan tool to remove the check engine code, because you're going to have to get rid of the check engine light and any viable codes for your test as well. So we're going to pull up our scanner here once again. We're going to head back into where we left off, right? We're going to make sure that the key is still in the run position, because it needs to be there. Make sure we don't forget that. It's got to be in run or it's not going to communicate with the scan tool. On the scan tool itself, you're going to go ahead and hit the back button. It's going to bring us up to the option to clear all codes read by code scan. So make sure, again, keys on, engine's off. Make sure it's off. It's not running. You'll be fine. And then you're going to go ahead and hit continue. Just like the code scan, this might take a tiny bit of time, so just be aware that you're going to have to close it. I'm going to jump forward in time here because I'm a time traveler. There it is. So code's cleared. So with the code's clear, you're going to hit OK. And then we're going to go and we're going to turn the car on. So we're going to start it. We're going to run it. So it should fire up. See it turn over there. Our check engine light should go away, and our gauge should read correctly. So that way we've cleared the check engine light. No check engine light. And the gauge is reading pretty good. So there we go. We've cleared the codes. We've set everything it needs to be. This is, in theory, good to ship for the problem we have. So we got code scan. And you got clear all codes. It's going to be your biggest deal right there for your test out. So let's go ahead and move on to the next section here. So for this next part, I'm going to walk you through a cluster failure. There's not going to be any sign-offs or work orders, so we're just going to go through the steps. I'm going to show you how we see a network failure when we kill all the power to the cluster and it just completely shuts down. That way you get a good visual representation of what happens, and then how do we walk through and see it with the scan tool, and then how do we reset it. So that's what's coming up next. So let's start out by actually setting the bug, which is going to be the last switch all the way on the right. Go ahead and flip it down. and that's going to put the bug in to kill the cluster. So go ahead and hop back into the car and make sure that you have your keys handy because you're going to need them. The scan tool should still be sitting there from the ECT. So go ahead and take the key, put it in ignition, put it into the run position, not start, but in run, and then watch. Aha, notice that the gauges will not come on because we've killed the input to them. So no gauges coming on is going to set codes, but we can't tell there's codes because no check engine lights. So all we're going to do is we're going to take the scanner as we have before, and we're going to go into code scan. Again, make sure that you double check that you have the 2016 Honda Civic selected. If not, you guys know how to find it. And then you're just going to go ahead and hit code scan, so that way we can scan and pull up some of the network codes here. You guys have seen this happen time and time again, so of course, I'm going to sort of fast forward through this, but it might take you about a good minute or two to pull up all the codes. So just be a tiny bit patient, and you'll be just fine. So the code scan done, I'm going to show you some new codes that should pop up. And the biggest one we're going to see is what we call U codes. So this one is U0104, and U codes are network codes. This is what we talked about earlier between all the modules that are connected. If you have a serious problem between the network communications, you're going to set U codes, like the one that says the PCM gauge control module. There's no communication between the PCM and the gauge control module because I've killed the power to the module with the bug. So it's throwing a network code that's saying, hey, the ECM and the gauge control module aren't talking, and they're not going to talk because they're not turned on. So that's what we're looking for the codes. Once you've seen enough and it's sufficient, you go ahead and click back. If I can get my button to work. At which point, we're going to go and reset the bug. So we're going to go, back out, and we're going to set it back up. So that way the power comes back to the gauge cluster, and we're going to guarantee that it turns back on before resetting them codes. Let's go ahead and flip the switch back up. There it is. Beautiful. Go ahead and head back to the car, and let's go take a look. See, now my gauge cluster's back on. So it's got power to it. If we put it back in, reset. Yeah, there it is. Gauges come back on nice and pretty. So that's what we're looking at for just a real simple see. If you have a gauge cluster that just fails outright, it's going to go black on this car. But we need to reset those codes before we go and put this tool away, return it back up front. So you're going to go to clear all codes, just like we did before in the ECT, hit continue, and wait for the codes to clear. So it's going to take a little while, so here I go. I'm going to jump forward in time because, I'm Time Lord here. And all my codes are cleared. So there we go. We're going to hit OK. That is if I can actually hit the button right. Yeah, there we go. So for this next coming part, I'm going to show you how to disconnect the scan tool. And this is super duper important because if you disconnect the scan tool wrong on some cars, you will either damage the scan tool or more likely you will damage the modules on the car itself. So do not skip this step. This is why this is in big red letters. So just be careful and aware. So let's go. So before we disconnect, we need to make sure that there's no active vehicle. So the active vehicle is the 2016 Honda Civic, and we're going to hit this button, which deactivates the vehicle we're working on. And you should see it disappear. It says no active vehicle. Now we are safe to disconnect the scan module from the scan tool in the car. This is the only time that it is safe, okay? No active vehicle. So once that's good, we can pop on down. See, we got the green light. We're still connected. Grab it and tug. Don't pull on the cable. Might have to wiggle jiggle it a little bit and then pull it out. Nice and safe. There we go. If we don't do this first, we have a very real potential for frying the modules. So be aware that you need to disconnect it first and then go return it. So you're going to go take your scan tool and your module and probably your DVM, bring it back to the front desk and return it before we finish out. Make sure you take your key out, and you're going to return this as well. And one last thing, before you return this, do not shut off the scan tool. Don't shut it off, keep it on. What's going to happen is they're going to dock the scan tool, and in this little port right here, they're going to keep it charged. So we keep it on, so that way students don't have to wait 4 or 5 minutes for this dinosaur of a scan tool to actually, turn on. It's a dinosaur, but it's from 2017. Yeah, it runs on XP. That's how slow it is. Just make sure you send it to the home screen, and you'll be safe. Okay, now go bring it back. So before we finish out this lab and we go to the conclusions in your packet, I'm going to give you some special notes about your hands-on test, mainly how the wiring system is going to work on the test, what sensors will be affected and what gauges, and how do we pull it up on the Mitchell on demand, because I'm that kind to pre-prep you for a test. So gosh darn it, I'm a great guy, and I know you appreciate it because I appreciate me too. So the test is going to concern a problem with the oil pressure light. So there's going to be a problem with that. And just like the ECT sensor or anything else, you're going to have to be able to get to the sensor, which is here on the back side of the engine. And this is going to be your test point. So you're going to have your scan tool and your DVOM. So if you do your DVOM check, this is where it's going to be at. And there's your test point. I'm also going to show you in ProDemand how we get to the wiring diagram of it, just in case you're confused. My vehicle selected, of course, is 2016 Honda Civic with 2-liter engine. We're going to go to one search, just like we did for the ECT. I'm going to say oil switch. Hit return, brings it up. You will see it is not on this list, so we're just going to select oil. And then it's going to give us OEM diagrams. Click on the diagrams, and we're going to get the instrument cluster. So if we scroll down, we're going to look in these boxes, see if we can find the oil switch. This is the econ switch, a radio switch. Then we're going to go to instrument cluster 3 of 4. And off to the right, 2-liter right side bottom, there it is. Oil pressure switch. We're going to click on that. We're going to zoom in on it. Zoomy, zoom, zoom. And there it is. So basically the switch is going to work, but the left side of the PCM is going to send power out, which is the pink wire in your case. It's going to go into this switch, and if there is no oil pressure, it grounds out, just like I showed you in the dummy light earlier, right? So as long as there's no oil pressure, it's going to ground out, then the light's going to come on. Once the vehicle kicks on, if oil pressure is good, it's going to lift this switch off of its seat, and the light will turn off. See? Just a simple idiot light. Just be aware, again, 1,000 times, you got to be careful with this. If you're going to test this switch, the engine needs to be on, needs to be running, engine needs to be turning. If you just put it to the run position with the engine off, you're going to get erroneous or strange readings. So make sure the engine's on when you're testing this. But that's how we're going to find it. Good luck on the test, guys. So here we are at the end of the conclusions. Hallelujah. Mary, Joseph, and Jesus. We made it. Okay, so conclusions. Number 1, gauges relay important vehicle information to driver. That's the purpose. The gauges themselves receive their information from sensors, which we sometimes refer to as sending units. Many modern gauges are connected to the sensors via the CAN, the closed area network, and their various modules. Be aware that the CAN system is important, and it is on all the vehicles, so we don't have directly wired sensors anymore. A failure in the sensor, module, closed area network, or the gauge itself will cause the gauge to read incorrectly, or in some cases, not at all. Number 5, super important. Dark Side of the Moon is good, but guys, it is super overrated. I highly recommend Wish You Were Here if you're looking for a Pink Floyd album. Number 6, most sensors in the vehicle only use 5 volts, which we refer to as a reference voltage. So you're not looking for 12, you're looking for 5. The reference voltage keeps it nice and steady so that the gauges read proper. Number 7, gauges are typically mounted into clusters, and on most vehicles, if a gauge fails, you have to replace the whole cluster. Some vehicles, however, will allow individual gauges to be replaced, usually high-end sports cars. So you're going to find, like, your M3s or M5s will occasionally have separated gauges on them. Number 8, always check for power or ground before you condemn a sensor, gauge, cluster, or module. Make sure they have power in, make sure the ground is good. Always double check the powers and the grounds, okay? So that's going to be a conclusion. That's going to wrap up this lab. Pretty short, less than about an hour and a half compared to the rest of them. So hope you guys enjoyed it. I look forward to seeing you at the next one. Good luck, guys.